Imperial College London, charge distributions of various substances. 1, 2, 3.
Cool. Yeah, so broadly, this is about charge distributions of various salts. I've been looking at salt aerosol predominantly initially, but I'll extend this into synthetic lung fluids, hopefully next year. Okay, so why is charge important? Electrical charge helps to make filters collect more efficiently. They deposit in different parts of the airways. They agglomerate differently in making nanostructures. That's important. And the known charge is assumed by these DMAs to characterize the size distributions. And if the assumption is wrong, then maybe DMAs are giving values on size distributions that are not quite right. And also in terms of weather, air pollution, and so on, charge is also important. So what affects charge levels? Well, the size of the aerosol is an obvious one. The larger they are, the more opportunities that they have to have higher charge states. The shape as well, that affects the corners where charges can collect, and the surface area. What they're made of may make a difference, and this is something that I'm investigating. And how they're made can affect how charged they are. And the industrial partner here is Dyson, and this is why they're interested in this, because charge states can affect how well they're picked up. So the way that I have been doing my measurements with this particular generator, this is a Collison nebulizer. I have a solution in here, and that blows air. I've been using nitrogen. That blows air into the nozzle, and that effect creates this aerosol. But with that mist, you get all sizes coming out. So they're also quite wet, and so the first step is to dry it. I've been using the silicate drying beads. That seems to bring the relative humidity down below the threshold for the different salts I've been using, to make sure that they are solid. Then I separate them with the AAC. This is a centrifugal drum, and it separates the aerosol that we had from the mist from the Collison into different specific aerodynamic diameters. And the reason that this is another really useful bit of kit is that it doesn't use electrical charge to separate like a DMA. So you've still got all of the original charge distribution coming out at the end. I have the option then to have a neutralizer turned on or off. This is a soft X-ray neutralizer. The reason for using this is because this is what the DMA uses to impart or impose a known charge distribution so that it can characterize properly. So I have it turned on, and then I have it turned off to measure or to see what the difference is between the charge distributions when they're created from the Collison and when they're neutralized. That then goes through this ESP, electrostatic precipitator, and that's essentially just a way to, it's an on and off thing. If you turn it on, there's a charge in there that, there's a high voltage in there that means that all of the charged aerosol gets taken out of the air. That means that you can measure the neutral charge fraction with a CPC at the end. Or if you have it turned off, then you get all of the charges coming through. So this doesn't separate between positive or negative. This is just a way to measure the neutral fraction. So that's the first thing I measured. The neutral fraction theoretically is this this dark line, and I measured this synthetic lung fluid. This is a mixture of salts and proteins. And interestingly, you can see when the neutralizer is turned off, in other words, the neutral fraction that you get just from the generator is lower than the predicted value, and you get higher neutral fraction when the neutralizer is turned on. Now that's interesting because it means that the equation used by the software in the DMA should be predicting this lighter blue and the dark line in the same place, but it doesn't seem to be in this case. So that's something interesting. I did it with some other salts, and they're consistently providing or showing the same pattern. So when I had the neutralizer turned on, they're consistently giving higher fraction of neutral particles than the theoretical values predicted. Then to measure the charge distributions, in other words, how many charge 1 states, charge 2, and positive and negative, I have the DMA. Just to indicate what's going on here. If you have your aerosol coming in from the top down to the bottom, and you have the central rod, then if the voltage is set just right, then you can get, in this case, a charge state of 4 plus, hitting that small outlet, and then that is counted. And then you change the voltage of the DMA to select the different sizes. And so I gradually changed the voltage of the DMA to see how many +1, how many +2, how many +3, and so on you were getting. When you change the voltage a little lower, then you get your smaller charge states. When it's turned off, you can get all of them coming out. And when it's positive, then you get the negative particles coming through. So this is the setup I had for the charge distributions. And this is an example of the data that I got. On the x-axis is changing the voltage of the DMA. And with the red is when I had the neutralizer turned on, and the blue is with the neutralizer turned off. And the left is the negative particles, which is the positive polarity of the DMA, and then the opposite on the other side. And you can see this is very symmetrical, which is interesting to see. So I was expecting maybe some of the salts would be asymmetric, but in all of the data I've looked at, they look pretty symmetrical, which is interesting. These peaks then represent the different charge states of the particles, and you get the same on the other side, but positive. And with that, red is the neutralized and blue is the charge state you get from the Collison. So the Collison nebulizer showed that you get more charge states coming through, and when you neutralize them, it reduces the charge states you get, but it seemed to increase the fraction that had one charge state. So how to compare this with the theory? By looking at the area under the graph, that tells you the proportion of the particles at each charge state. And if I plotted that on with the theoretical values, the theoretical values are found from this equation, and this was updated in 2015 for a soft X-ray neutralizer, which is slightly different to how it was done before. But this equation only goes up to a charge state of 2. There's a slight imbalance between the positive and negative due to the mobility of the positive and negative charges. So this is with the neutralizer being turned on, and you'd expect all the data points to see exactly where the theory is for the DMA to be accurately characterizing the sizes. But here you can see that there's a good 10% extra of the neutral fraction appearing with this sodium chloride 0.1% solution. I repeated it with some other salts. The CC is choline chloride. The reason I use that is simply because I misread the bottle. But it's interesting because it's provided some interesting data which I wouldn't have got otherwise. So that's a happy accident. The AS is ammonium sulfate. And I use these salts because they're commonly found in synthetic lung fluids. But you can see also, like in all of the different salts I've looked at, that consistently that neutral fraction is above what is predicted by around 10% in most cases. So I also plotted the difference then between the theory and my measurements. And that dotted line is 0 difference. And interestingly, with the neutral fraction, it's greater differences at the start and then it goes down. But I think that's just because the values get smaller. I should really make this not an absolute difference, but maybe a scaled one to make a bit more sense. But this is only what I did a couple of days ago. And I repeated that difference with all the different salts, but it's kind of exhibiting this very similar behavior. You can see with the charge states of plus and -1 that they're all going up as it gets in larger size. As I said before, like these should all be 0, and for the DMA to be giving the right values. Another thing to look at is where the peaks are, rather than the area under the peaks, is to say where are the peaks, and that's kind of useful in working out the effective density as well. The effective density is worked out by looking at the mobility diameter, the position of that first peak, and that's what I worked out here. And as the particles get bigger, the effective density gets closer to the line, which is the bulk density, which kind of makes a lot of sense, except for this choline chloride. The bulk density, what I found online, was 430, and that seems to be getting bigger. It seems to be deviating away from the value that I found. I think this one I'll need to find a better bulk density for. But all the other ones seem to be, as the particle gets bigger, it gets closer to the bulk density. And put all together in one plot, you can see that they're all kind of following the same trend. What to do next? I'd like to try to do different generation methods. The one I've been using is the one on the right, this Collison. But really to find out how does a synthetic lung fluid, how does the charge state get affected by producing it with a kind of a larynx? Does speaking or singing or producing aerosol in that way, does that impart an electrical charge on the aerosol? And if so, can that help to remove breath aerosol from the air for the next pandemic or whatever this one leads? And also this Topaz aerosol generator is something that Dyson has, and maybe I can play around with that to see what the charge distribution is creating aerosol in this way instead. And this is a dry aerosol generator. This is a wet one. Another thing I'd like to see is the size and the shape of these aerosols. Maybe I can look at them with a electron microscope. That might help to explain the charge distributions that I'm seeing. Maybe the shape or the size of maybe the shape of the crystals changes as you get larger. And following from this, more questions I have. When I'd like to try the synthetic lung fluids, and if I improve the recipe, does that change the size distributions or the charge distributions or the electrical mobilities? If I improve the generator, in other words, make some kind of larynx that works in a way that produces aerosol by kind of moving these two silicon folds, proves to be a bit logistically quite difficult to do that. But if I do, then that'd be quite interesting to look into. And if I know what the charge and size distributions are of these synthetic lung fluids, could they be taken out of the air better with filters? And I'll leave it there if anyone has any questions.
Great, thanks, Pete. We have a few questions in the room. One.
Thank you, Pete. Louis from University of Hertfordshire. I got a question regarding when you factor in your neutral fraction, you factor in potential losses in the ESD. In other words, is it possible that some particles that are charged effectively pass through the ESD?
Okay, Jonathan, I'll have to ask you to repeat the question. I heard something about neutral fractions, but that's all I managed to get.
Yeah. So, am I just repeating the question?
Yeah.
Okay, so is it possible that perhaps there is some losses in the ESD that would that you haven't factored in, and that would explain why the neutral fraction might be higher than the theory?
Okay. So the question is, in the ESP, are there losses you're not accounting for?
Oh, okay. So the losses would only be an issue if there are greater losses for different charge states. If the losses are all consistent between every charge state, then it's not a problem, because I'm looking at not the absolute value that I'm getting, but the fractions between each charge state. So yeah, I'll be getting losses throughout all the parts of the system, but it's only if those losses are different with different charge states where that's an important factor. I don't know if that's the case, and it's a valid question, but I assume that the losses are going to be consistent.
Another question in the room?
So your salts are crystallized by the time you're analyzing their is that right? I was wondering how long they took to do that from your sort of solution that you analyzed.
Okay, so the question was, how do I know if the salts are crystallized?
So how long do they take?
So,
Well, I don't know how long they take to crystallize, but I've looked at the relative humidity after the dryer, and that relative humidity seems to be it's under 9%, and as I understand, that is below the threshold required for the salts to crystallize. But what is a possibility is if there's a larger aerosol, there might be water inclusions within the crystal. And I would expect that to be picked up from looking at the effective density. So if the particle has a water inclusion and I measure the effective density, I'd expect it, as it gets larger, to get closer and closer to 1,000 kilograms per meter cube for the density of water. But I can see them actually deviating more towards the bulk density. So from that, I am making the assumption that there are no water inclusions and that they are solid crystals.
I have one quick question, Pete. Why synthetic lung fluid? Why not do the measurements on real exhaled aerosol?
Yes, the reason is because the measurements currently take 20 minutes or 40 minutes. So I'd need to have someone with lungs the size of a whale's to measure this. And another issue is that by any kind of small deviation in the signal strength affects the number concentration. And so I need the signal to have a very, very constant number concentration coming out of it over the scan. And this is another part of the logistical problem of designing a larynx, because the signal strength, the particle number concentration needs to be constant for these to produce meaningful data.
Great, thanks, Pete. There are a couple of questions in the chat. Maybe you could answer those for the benefit on.
Oh yeah, sure.
And we'll break there for the tea break.